Hello stats fans, and welcome to chapter 4 where we start talking about probability. So in order to understand statistics or even work with statistics, we have to understand probability first. So we will cover probability in chapter 4, and then we'll move on and use probability when we learn about statistics. So probability is a numerical measure between 0 and 1 that describes the likelihood that an event will occur. So here's how we read this statement. This says if the probability of event A is 0. So event A could be anything. It could be the event that it rains today, or the event that you pass your statistics final exam. Could be anything like that. So we read it as if the probability of event A equals 0. And if that is the case, then event A will not occur. If something has a probability of 0 of happening, it means it's absolutely not going to happen. On the other hand, if the probability of event A is 1, then event A will occur. So these are the two extremes, 0 and 1. Probability of 0 means it absolutely will not happen. Probability of event A means it absolutely will happen. And probability will be some number between 0 and 1. So it's not going to be a negative number. It's not going to be 1.7. It's always between 0 and 1. And the only way you can really get out of that is if you use percentages, and then it will be between 0% and 100%. And all that is you're taking a decimal number and changing it to a percent, right? So you move the decimal 2 places to the right and put a percent on it. But if you write it as a decimal, it's always going to be between 0 and 1. So probabilities closer to 1 indicate the event is more likely to occur. Probabilities closer to 0 indicate the event is less likely to occur. So as an example, we could have something like this. The probability, now in this parenthesis I could write out the event, or I could do like this and say event A and define event A somewhere else. But you could do it like this. You could say the probability that Kurt will enjoy the next faculty meeting equals, okay, this one is super easy. There's only one answer that works here, and that is a big fat 0. It's not even 0.001, it's just plain old 0. That means that this will not occur, right? So this is just a different way to write it. You can say probability and then in parentheses write your event, or you can write it this way where you define the event somewhere else. Okay, so we have to consider how probability is assigned. And there are 3 main ways. There's actually a 4th one that our book doesn't cover, but that 4th one is Kolmogorov's probability axioms. So I'll just write this one down here. So he was a Russian mathematician, and he tried to establish axioms for probability. Like when you take geometry, there's certain axioms which are basically statements that are regarded as being true. So our book doesn't cover that, but our book covers the main ways that probabilities are assigned. So we'll look at those 3 main ways. And maybe some of you who are super lucky will take stats maybe in grad school or a higher level class where you look at these Kolmogorov's probability axioms. But for us, number 1, the first one to look at is intuition. So intuition is a way of establishing probability where you incorporate past experience judgment or opinion to estimate the likelihood of an event. So this one will say right away, okay, this is not very precise. Of the methods that we look at, this, oops, you better spell it correctly. Of the methods that we look at, this is the least precise method. And you'll see why as soon as you do an example. Here's an example. The probability that the Lions will beat the Bears whenever they meet again is blank. Well, you would probably agree that there is no mathematical algorithm that can give us a reliable number here, or no computer model that's going to be really reliable. So basically we would have to just use our experience. Maybe the last 80 years of Lions football could help. But we use our experience and just try to come up with a probability that the Lions will beat the Bears. Some of you may be diehard Lions fans and we'll put a 1 right here. Or some of you may be used to watching the Lions and may put a number closer to 0. But we basically come up with a number to put here. And we're just using experience, judgment, opinion, things that we know about the teams at the time, and we would come up with a number. So I'm just going to put something here. Let's go with, let's say 0.4. It's just a number. Now, some people are better at coming up with these than others. So the Las Vegas odds makers, they make their living coming up with these numbers, just using what would be called intuition. So not very precise, as you can see, but sometimes that's all we've got. We just have to use intuition here because we don't have a better method. Okay, so intuition, not very precise, but it's one way that we can assign probabilities. Another way is to use relative frequency, which is oftentimes called empirical probability. And when you see this word empirical, think of experiment. So these are probabilities of events kind of found by experiment, actually. So the probability of an event is equal to the relative frequency. We've got this little formula F over N. So what this means is this is the frequency of the event out of a sample of N observations. So that's what that formula means there. We're going to do a little experiment. And sometimes you'll see this notation like this. The probability of event E is equal to F over N. There's nothing special about whatever you put in. You can call the event anything you want. But this, remember how this reads, probability of event E is F over N. So let's look at a quick example to make sense of this. So let's say you choose 50 students randomly from GRCC. So we just choose 50 students randomly. From GRCC. And we find out that 24 are male. So 24 of these 50 students are male. So what we could do here, we could come up with a relative frequency. We could say the probability of being a male student. So if I randomly choose a student out of the population of GRCC students, the probability that I would choose a male student would be 20, would be, let me put the formula here, F over N. The frequency of students who were male were 24. Out of the number of observations, or our sample size is 50. which is about 0.48. So doing this experiment, if you wanted to figure out the proportion of students who are male at the college, which is another way of saying the probability that I would choose a male student if I chose one student at random, it would be 0.48 based on this. So there's something called the law of large numbers that we'll talk about in a little bit. Let me just write this down here because it has to do with this. The law of large numbers, which is one of the more important theorems in statistics. The law of large numbers basically says choosing 50 students randomly is better than choosing 10. And choosing 1,000 students randomly is better than choosing 50. So basically just think of like at any one time in the semester we have, let's say, I'll just make it easy, 15,000 students. Let's say we have 15,000 students for in the entire college for a particular semester. So the law of large numbers says basically the closer we get to this, the more likely we'll be to be accurate. Because if our sample size was so large that it was 15,000 students, then we'd have the entire population and we would know exactly what this is, right? So the law of large numbers, generally speaking, says the larger the sample size, the more accurate you're likely to be. It doesn't mean you have to be, but you'd be more likely to be. So like, here's an extreme example. Let's say your friend is really bad at statistics and your friend is like, well, I'm going to figure out the probability that, figure out the proportion of students who are male students, and your friend just interviews 2 students and they're both males. He chooses 2 names at random, they're both males, and he's like, oh my god, it's 100%. All students at GRCC are male students. And you probably know right away that that's your friend is not understanding how statistics work, because a sample size of 2 is not enough, right? So law of large numbers, we'll talk about a little bit more, but generally it makes sense. It's something you would just instinctively know without me mentioning there's a name for this thing, right? And then the relative frequency or the empirical probability, remember empirical is from experiment. So relative frequency is just this, you just do a little experiment and whatever your results are, you use that for your estimate of the probability. Okay, so we've got intuition, we've got relative frequency, and now we've got our third one, which is equally likely outcomes, sometimes called classical probability. And the reason it's called classical probability is because when probability was first being studied, if you remember, it was originally studied to answer questions, gambling questions, about card games and dice games. So this is what's called classical probability. In some texts, our textbook calls it equally likely outcomes, but they're the same. These refer to the same thing. And this is a very precise way of finding probability. And this, out of the 3 ways we look at, this way we'll all get the same answer as long as we don't make any mistakes. By intuition, of course, we're going to get different answers. Relative frequency, we'll get somewhat different answers, but if we do things well, we should get close. But equally likely outcomes or classical probability, we're going to all get exactly the same answers. So we can use this formula. The probability of an event is the number of outcomes in which the event occurs over the total number of outcomes. And the little note here is this is the most precise type of probability. Probability. It is calculated by taking all possible outcomes into account. Okay, so here's an example. You'll see this makes perfect sense if you look at one example. Let's say we have a fair die. Remember, six-sided dies. Sorry, Dungeons and Dragons fans, we're just going to stick to six-sided dies. So if you have a fair die, and somebody says, what's the probability that you're going to get a 4? Well, if we have a six-sided die and it's a fair die, then the probability we get a 4 is 1 out of 6, right? There's 1 4, and there's 6 sides. What about the probability that you get an even number, or the probability that you get a number greater than 4? Greater than 4. Okay, well, hopefully when you looked at this, you said, okay, how many ways can I get an even number? What are the number of outcomes in which this event occurs? Well, this event occurs if you get a 2, a 4, or a 6, right? So there are 3 ways it can occur out of 6. You can leave 3 over 6. You can reduce if you want to 1 over 2, or for the decimal fans, 0.5. So any of those are correct. Normally in my classes, I always say to reduce, but with probabilities, sometimes we need to later add these together, and you might need a common denominator. So when it comes to probabilities, I'll let you guys do what you want. You can leave it any of these ways. What about a probability of getting a number greater than 4? Now this, we have to know, this means greater than 4, not greater than or equal to 4. Remember a little review here. Greater than or equal to, greater than. So if we want it to be strictly greater than 4, it has to be 5 or 6, right? Those are the 2 outcomes in which this event occurs, a 5 or a 6, which means there are 2 ways that can occur out of 6, or 1 over 3, or 0.3 repeating. Then we've got a little box here with a note, and this is going to be really important for us to keep this in mind. Put a little star here. If you keep this in mind, a lot of times you'll be able to tell if you've made a mistake in one of your calculations. And here is the note. The probability of event A, no matter what the event is always less than or equal to 1 and greater than or equal to 0. Right? So this probability, no matter what it is, no matter what event A is, the probability of event A is always going to be greater than or equal to 0, less than or equal to 1. Right? So the probability is never going to be negative. It's never going to be 2.5. It's always between 0 and 1. With one little warning, if you write it as percentages, it's going to be between 0% and 100%, but it has to have the percentage with it if you're going to do it this way. So normally you see probabilities written as decimals, but a lot of times when people speak of probabilities, they speak in terms of percents. So just remember the way you convert Michigan sales tax is 6%. And to figure out your tax, you would multiply what you buy by 0.06, right? So 0.06 is 6%. So to get from a decimal to a percent, we move this twice to the right, once, twice, and then we add the percent. Okay, we also need to know about a complement of an event. The complement of event A, written A complement or A prime. Our book uses this notation. It's probably the most popular notation, A with a superscript C. You also see sometimes this A prime. Our book doesn't use this, but if you ever see this referring to A complement, this is like a little prime, like in calculus you'd use for a derivative, little slanted line. So the complement of an event, A complement, is the event that A does not occur. So whatever event A is, maybe event A is it will rain today. Well, then event A complement is it will not rain today. We can use a Venn diagram to show this also. So the sample space, we'll get into more detail about what a sample space is later, but it's basically the set of all the events that can happen. So when it comes to A and A complement, event A could either happen, which would be here, or not happen, which would be here. So event A has to either happen or not happen. So you can think of a Venn diagram as being, this is event A here. Anything that's not here is out here, which is event A complement or not A. And then there's a few notes here. So if I were to say, before we talk about this note, let me just say, let's say I were to tell you the probability of A equals 0.4, and I tell you that the event A is it will rain today. Then if I asked you what's the probability of A complement, and I said, so the probability of rain is 0.4, what's the probability of no rain? And you would say 0.6, right? Because you know that if there's a 40% chance of rain, that means there's a 60% chance of not rain. So you automatically think of 0.6 because you know this has to add up to 1, and that's what this first note says. This says the probability of event A plus the probability of event A complement has to be 1. So A is either going to happen or not happen. So if you add these two probabilities together, you have to get 1, just like we did here. 40% chance of rain means a 60% chance of no rain. So another way you can think of it is you could figure out the probability that A does not occur, which is really the probability of A complement, right? And then you can get this formula just from here. So some of you guys who are always saying, you know, Kurt, I sure wish we do more algebra in this class. Here is your lucky day. So thinking of the good old days in algebra, if I wanted to solve this equation right here, it's an equation, right? If I want to solve it for this thing, couldn't I just subtract this thing from each side? So you would go something like minus probability of A, subtract that from the left side of the equation and subtract it from the right side of the equation, which would make that cancel, and you would get the probability of A complement is equal to 1 minus the probability of A. And that's exactly what this says right here. I was just using algebra on this equation to get here. So this note 3 is going to be really important for us when we get into chapter 5. So it's introduced here, but we use it a lot in chapter 5. So we have to know the complement of at least one success is no successes or zero successes. So in other words, if you can't say at least one, there has to be none, right? Because think about, let's say you're going to take 10 free throws. And so if you don't make at least one, so you're going to take 10 shots. Not shots like we take before the faculty meetings to dull the pain, but a shot like a basketball. You're going to shoot at a basket, you get 10 free throws. So if you can't say you made at least one, doesn't that mean you made none? Right? So the complement of at least one is 0. And we will use this all the time. So if I combine this statement with this up here, this is what we'll use in chapter 5 quite a bit. Yep. Put this in red because this will come up a lot. We're going to say the probability of at least one success. The probability of at least one success is 1 minus the probability of 0 successes. And that's just combining these two. The complement of at least one is none or 0. And then we use this formula. So the reason this is going to be really important for us is because we're going to find out in chapter 5 that when you say at least one, that means there could be 1 or 2 or 3 or 4 or 5 and so forth on to how many trials you have. So figuring out the probability of at least one, if you do it like that, you're going to have to figure out the probability of 1 success and then probability of 2 successes and 3 successes and add them all up. But it's going to be way easier to just figure out the probability of no successes, the probability of 0 successes, and subtract it from 1, because these are equivalent to one another. So this is just kind of a heads up for what we'll be seeing soon. And it might, if you haven't seen this idea before, it might seem a little confusing now, but it'll be a lot less confusing when we do this in chapter 5. So it's just kind of a little heads up. So when I mentioned in chapter 5, it'll seem somewhat familiar because we just talked about it right here. So it's going to be important for us a little bit later on. So before we get into a lot of details of probability, we have to be familiar with some of the terms. So let's just look at some of these. So we've got probability. Probability is a field of study that makes statements about what will occur when samples are drawn from a known population. So we know about the population. We know the overall description of the population. The central problem is to compute the likelihood that a specific outcome will happen. So here's an example of probability. Let's say you know the makeup of a deck of cards. You know there are 4 suits, there's hearts, diamonds, spades, and clubs. So you know there's 4 suits of cards. You know there's 52 cards, 13 cards of each suit. And you want to figure out, if I pick one card, what's the probability that I get a heart? So that would be like a probability question. We know about the population, and we just want to compute the likelihood that a specific outcome will happen. Okay, so now statistics is a field of study that provides methods for organizing and summarizing data. And that's what we've done so far, that's descriptive statistics, and for drawing conclusions based on information contained in the data, which is where we're headed for inferential statistics. You know only the results of a sample drawn from the population. So we have this sample, but we don't know much about the population. The central problem is to describe the sample, which again, that's descriptive statistics, and draw conclusions about the population based on the sample results, which is inferential statistics. So an example of this is, let's say your friend is visiting, and maybe your friend is from some other country where they don't play cards ever. Your friend has no idea about what a deck of cards is. And you allow your friend to draw samples and then try to infer what the deck of cards is like. So your friend maybe gets a sample of 4 cards and then tries to put together the pieces about the entire population, the deck of the cards. Okay, that's statistics. And then we've got an experiment, and there's a whole bunch of words that mean the same thing for us. Experiment, statistical experiment, observation, trial, all these mean the same. This is any random activity that results in a definite outcome. Usually the outcome is in the form of a description, count, or measurement. So some of you may have had chemistry class where you get to do some kind of cool experiments, lighting things on fire, mixing chemicals together to see what happens, tasting chemicals. Well, hopefully you don't do that. But you get to do some cool experiments. But for us, not so exciting. Here's examples of our experiments in stats class. We will flip a coin. We may roll a pair of dice. And if we're feeling really crazy, we may even draw a raffle ticket. That's only on special days. So those are the experiments we're going to see. Not super exciting, I know. But that's what we've got. And then some other terms that have to do with this experiment. An outcome is each individual result that is possible in an experiment. So each individual result that's possible in an experiment. So if I roll a 6-sided die, there's 6 outcomes: a 1, a 2, a 3, a 4, a 5, or a 6, right? Those are the outcomes. An event is a collection of one or more outcomes of an experiment. So an event could be, I roll a 6-sided die and get an even number, right? That would be a collection of outcomes of getting a 2, a 4, or a 6. And a simple event is one particular outcome of an experiment. So basically, a simple event is an outcome. So you can use those pretty much interchangeably, simple event or outcomes. As long as you know a simple event is one particular outcome. Now, a sample space, this is a set of all possible simple events or outcomes of an experiment. And when you see sample space, I'm going to make a little room here. It will be typically, there's an abbreviation for it. Our book uses a capital S always. And this is sample space. And then we'll put set notation. It always has these brackets that you use, probably have seen in maybe geometry class for sets. So the outcome consists of this set, or sorry, the sample space consists of this set of outcomes. So this could be the sample space for rolling a 6-sided die. Now our book always uses this S, but you'll also see in other books will use this capital omega that means the same thing. So if you ever see this or this in statistics, it typically is referring to a sample space. This is what our book will use. So if we're asked for the sample space, you're going to want to use these brackets from set notation. So just to make sure we're doing okay here, I have a couple of real simple examples. I want to point out something that we'll notice about these. So let's say we've got this experiment. This experiment will be flip one coin. So we flip one coin, and we could figure out the probability of heads or probability of tails. In other words, that's everything that could happen, which means if we wanted to, we could say, here's our sample space. We could say S equals heads, tails. Those are the only two outcomes, right? So that is our sample space. So again, we use this notation here for set notation. So we have these braces like this. We use capital S for the set. That represents the sample space. So if we want to figure out these probabilities, well, assuming that it's a fair coin, the probability of getting heads would be 50%, right? 0.5, 0.5. Or if you prefer fractions, 1/2 for each of them. And then notice this, if we add these up, we get 1. But if I add 0.5 and 0.5, I get 1. So the sum of the probabilities of each of the outcomes in the sample space equals 1. And we'll see soon that that's always going to be the case. So let's see another one. Let's see, we've got this other experiment. This one is we're going to roll one die, a fair die, 6-sided die. And we could figure out the probabilities of all of these things. Right, if it's a 6-sided die, this is everything that could happen, right? You could get a 1 through a 6. We already talked about the sample space. Here's the sample space right here for this experiment. When you do this experiment, each time you perform this experiment, you're going to get one of these, right? 1 through 6. And if it's a fair die, these probabilities are all the same, right? 1, 6, 1, 6. For a fair die, there's an equal chance that each one of these sides will come up. And if you roll these, again, we get a 1. And just want to make a note about these. The sum of the probabilities is 1. The sum of the probabilities is 1. So if we add up all the probabilities of all the outcomes in a sample space, we get 1. Okay, so moving on here. I think everyone listening should be able to put the next 3 things here. The probability of event A is always going to be less than or equal to 1, right? And it's going to be greater than or equal to 0. So you already know that. So if you're doing any homework in pretty much from here on out, and you're figuring out a probability of an event, if you get a number not between 0 and 1, something wrong happened. Right, so if you can keep this in mind, you'll save some mistakes coming up, some common mistakes, by just saying, okay, can I get a probability of 1.7? And you can't. It's got to be between 0 and 1. And then also the sum of the probabilities of all simple events in a sample space must equal, hopefully you're thinking 1, right? That's what we just talked about. So if we take all the probabilities of all the simple events in a sample space, or in other words, all the outcomes in a sample space, if we add up all these probabilities, we're always going to get 1. And the law of large numbers, this is something we talked about before, just says that as the sample size increases, the relative frequencies of the outcomes get closer and closer to the actual value. Right? So if you want to figure out the average age of a GRCC student, and let's say there's 15,000 students. Well, if you sampled 50 of them randomly, you'd get a number, right? You could figure out the average age of 50 students. But what if you sampled instead 14,000 of them? Wouldn't this, if they're chosen randomly, wouldn't this probably be really, you could be pretty confident that this is going to be really close? Because in general, the larger the sample, the better off you're going to be. So if your sample were so large that you had the entire population, that your sample was the entire population, you would have the exact or actual value. So this is just saying, generally speaking, as the sample size increases, these relative frequencies of the outcomes get closer and closer to the actual value. Now you'll find out, we've already talked about, like for polling, even though there are 340 million Americans, you don't have to poll all Americans to get an accurate description of how people are going to vote. You just need about 1,500. So as long as you're careful about your samples, you don't need a sample of 14,000 to be accurate about 15,000. You could probably get pretty accurate here with about 50 if you're careful. So keep that in mind. This is just generally speaking. The law of large numbers says bigger samples are better, but that doesn't mean we always need big samples. We usually don't need big samples as long as we're sampling properly. Okay, so that will get us through pretty much all the homework, but there's some homework problems I want to look at just to make sure we're on track. So we're going to go over a few of them. One thing I will mention also, there's a summary in the book on page 149. And when you get a chance, you may want to take a look at that. So that is, it's towards the end of 4.1. There's just a little box in the book that says summary, some important facts about probability. And it's stuff that we've talked about, but sometimes just rereading it in somebody else's words sometimes just makes it sink in a little bit better. So if you get a chance, take a look at this. And now let's take a look at some homework problems. So we've got problem number 2 in the book. This one's going to be too easy for you guys. But it says, suppose the newspaper states that the probability of rain today is 30%. So the first question is, what is the complement of the event rain today? Well, the complement would be no rain today, right? This statement is the complement of rain today. no rain today, or it will not rain today, however you want to say it. What is the probability of the complement? So if you want to know what's the probability of no rain today, well, it says the probability of rain is 30%, so the probability of no rain today would be 70%, or 0.7. You can use either one of those you want to. Since they said 30%, I'll use percentage too and say 70%. Then number 5 says, a Harris poll indicates that of those adults who drive and have a cell phone, the probability that a driver between the ages of 18 and 24 sends or reads text messages is 0.51. 18 and 24, that's a lot of you guys. 18 and 24, I know nobody would ever do that. That actually seems really low, 0.51. I think this might be old data. But it says, for those adults who drive and have a cell phone, the probability that a driver between the ages of 18 and 24 sends or reads text messages is 0.51. Can this probability be applied to all drivers with cell phones? So in other words, what about the probability for 18 to 24? What about 78 to 84? Do you think that 78 to 84-year-old drivers who have cell phones text with the same probability while driving as 18 to 24? Probably not, right? So they're speaking to this idea of generalizing results, which we don't want to do. We don't want to generalize like that. If this study was done on drivers between the ages of 18 and 24, we don't really want to generalize that to other age groups. So if we wanted to know, like for senior citizens, we would want to do a new study involving senior citizens. So we don't want to generalize results. And let's see, some of these are too easy for you guys. Okay, number 10 is a little tricky sometimes. So number 10, this one is a homework problem, so there's a spoiler alert coming. So if you want to plug your ears or fast forward. Number 10 says the sample space consists of 4 simple events, A, B, C, and D. Which events comprise the complement of A? Can the sample space be viewed as having 2 events, A and A complement? Okay, so I'm going to... Actually, you know what? Let's do it. I'll do it a little bit differently. Let's make it like a circular. And let's say we've got... Here is A, B, C, D. Let's think of it as one of those things with a spinner on here. So we've got this little spinner that will spin around. You know, you flick it with your finger, it'll spin around and land on one of these. So this is right here. This is the event A. So you flick this spinner around, you know, and it spins around here, and here's event A. Here are these other events, B, C, and D. So it says the sample space consists of 4 simple events, A, B, C, and D. So here is the sample space. Oh, that's very ugly. A, B, C, and D. So that's our sample space. I'm going to redo that one. So it says, which events comprise the complement of A? Well, the complement of A is anything that's not A. So the complement of A is all of these, right? Complement of A is events B, C, and D. So can the sample space be viewed as having 2 events, A and A complement? And yes, it can, because we could think of it like this. We're going to consider all of this here as being A complement. Right? So we're going to just think of all of this. If you get B, C, or D, all of this we're going to consider A complement. right? So we could say A complement consists of the events B, C, and D, basically not A. So that's what they're getting on number 10. Then probably the most important one for us is number 12. But before we do that, let's look at a much simpler one, number 13. Number 13 says this. It says, on a single toss of a fair coin, the probability of heads is 0.5 and the probability of tails is 0.5. If you toss a coin twice and get heads on the first toss, are you guaranteed to get tails on the second toss? Well, anybody who's been on Earth for more than 2 weeks knows that no, you're not guaranteed. And the reason I mention this is because this is referred to as gambler's fallacy, where sometimes gamblers will lose money because they'll have a string of, say, bad luck or bad cards, and they'll just be thinking, well, it's got to change. I've had all this bad luck. My luck has to change. It's just not true. These are independent events, which we'll talk about pretty soon here, but they're independent. So if you toss a coin, whatever you get on that coin toss has no effect on your next coin toss. So that's what they're getting on that one. But the one that I think is probably the most important for us is number 12. So, all right, we're done with number 13. Let's look at number 12. So number 12 says, consider the experiment of tossing a fair coin 3 times. For each coin, the possible outcomes are heads or tails. So part A says list the equally likely events of the sample space for the 3 tosses. Okay, so here's part A. So the sample space, so we're going to flip a coin 3 times. Well, this is what we could get. We could get, let me move it down here so we have enough room. So we could get 3 heads, right? Or we could get 2 heads and 1 tail, and that could happen any of these ways. It could have been a tail, then a head, then a head. Or it could have been heads, tails, heads. Or it could have been heads, heads, tails. In other words, the way we have these in order is this is the first toss, second toss, third toss, right? So to get 2 heads and a tail, it could have happened in any of these ways. Meaning the first coin toss was a tail, or the second one was a tail, or the third one was a tail. Then, of course, we could have got 1 head and 2 tails, and that could happen any of these 3 ways. And finally, we could get all 3 tails. So this is everything that could happen. This is our entire sample space if we're going to flip a fair coin 3 times. Right, this is everything that could happen. So let me just add these up. So we could get 3 heads or 0 tails. I'm going to talk about these in terms of tails because the book's going to ask us about that in a second here. We could get 2 heads or 1 tail, any of those 3 ways. In any of these 3 ways, we could get 1 head or 2 tails. Finally, this way we get 3 tails. So part B says, what is the probability that all 3 coins come up heads? And then it says, notice that the complement of the event 3 heads is at least 1 tail. Use this information to compute the probability that there will be at least 1 tail. So what we'll do is I'm going to show you how to do this 2 ways, the easy way and the hard way. Now, because this set is so small, the hard way won't seem that hard, but this is what will make Chapter 5 much easier if we understand this concept. So for Part B, they want us to figure out what is the probability that all 3 coins come up heads. So in other words, what's the probability that we get 3 heads? Well, there's only one way that can happen. Just looking at this list here, see, generally speaking, our problems will be way more complicated than this, and we would never list them out. There could be thousands of ways to list these. This is a really simple one where we can list them out. So this question is easy. The probability of getting 3 heads, it's right here. Just 1 out of 8, right? It's the only way we can get it out of the 8 possible outcomes. So the probability of getting 3 heads is 1 out of 8. So then they want us to use this to figure out the probability that there will be at least 1 tail. Again, this is where there's an easy way and a hard way. So I'm going to first show you the hard way. So let's say this is the hard way to figure out the probability of at least 1 tail. Well, think about what at least 1 means. It means there could be 1 or 2 or 3, right? That's the most because we've got 3 coin flips. So the hard way to do this is to figure out each of those probabilities and add them up. So the hard way is to say, well, at least 1 means we could have got 1 tail. We could have also gotten 2 tails, so we need to add that in. We could have also gotten 3 tails, so we need to add that in. So then what we need to do is figure out this probability, and this probability, and add them up. Now again, because this is such a small, easy sample or example of a problem, this isn't, even though it says hard way, it's not going to be that hard. But just think if we were going to flip the coin 37 times and it says at least 1. Well, then we need to go a long ways, right? We need to keep going all the way to 37. So keep that in mind. That's why this is in later chapters when this gets more complicated. This is definitely not the way to do it. This is like a brute force method. We just go straight ahead. At least 1, okay, 1 or 2 or 3, and we add them all up. So it's not too bad in this example. They're probably getting 1 tail. Well, that's right here. There's 3 ways to do that, right? 3 out of 8 outcomes. So this is going to be 3 out of 8 plus the probability we get 2 tails when we flip a coin 3 times. Well, here's those cases where you get 2 tails. That happens 3 ways, again, out of 8. So that's going to be 3 out of 8 plus the probability of getting 3 tails. Well, that's just here. It's just one way that can happen, 1 out of 8. So we would add all those together. And then that would give us 7 out of 8. Okay, so that's the hard way to do it. Again, it doesn't seem that hard because it's a simple problem. But in Chapter 5, you definitely don't want to use this hard way. What you want to use is the easy way, which we'll look at now. So here is the easy way. We're going to answer the same question. We're going to figure out the probability of at least 1 tail. And let me write this answer over here so I have a little bit more room here. I don't know why there's such a delay on this eraser. Okay, so here's our answer, 7 over 8. Now let's do it this way. So at least 1. So if you remember from that, we had those 3 rules for probabilities, and I've mentioned that if you have the probability of at least 1, it's much easier to instead say 1 minus the probability of no tails. So, okay, let me go back and find what I'm talking about here. That is right here. They're going back to here. Probability of at least 1 success is 1 minus no successes. So we're using this right here. We're going to go 1 minus none, basically. So let's go back down here and make use of this. So 1 minus no tails, that's going to be 1 minus, well, the probability of no tails, that's right here, right? Or in other words, 3 heads. Probability of no tails is 1/8. So then we would subtract those and get the same thing, 7/8. So the difference is, here's the important part. when we did it this way, we had to figure out probabilities 3 times, 3 probabilities. And these were easy enough, but usually when we get into more complicated problems, these will not be easy to figure out, so they each take a little bit of time. And there could be a lot more than 3. So here we just go right through, we figure them all out, add them all up, and get our answer. But here we only had to calculate 1 probability and then subtract it from 1. So that's why this works. But sometimes students are still not really convinced yet. So I'm going to show one more way that makes this a little easier to see. I'm going to make a little table here. So this is our outcome X. This is the probability of X. We could have 1 head, 2 heads, 3 heads, or 0 heads. So actually, you know what? Let me do this. Let me undo a whole bunch of this. Let's not do heads. Let's do tails. So you could have 1 tail, 2 tail, 3 tails, or 0 tails. So we figured out if this is our outcome and this is the probability of the outcome, the probability of 1 tail, we said that's 3/8. Probability of 2 tails, oh man, I messed that up. Okay, the probability of 1 tail is 1/8. Probability of 2 tails is 3/8. Probability of 3 tails is 3/8. Probability of 0 tails is 1/8. Now we know this has to add up to exactly 1, right? Because these are all the outcomes in the sample space, and if you add up all the probabilities, we have to get 1. So that's kind of why we can do this 1 minus idea. If this is probability of at least 1 tail, so it wants us to find the probability of all of these at least 1 tail. That's at least 1 tail, right? Well, couldn't we instead, since we know that if I add up this number here, whatever it is, to this number, I have to get 1. So instead of calculating all of these, we could just go 1 minus this. That's basically what this is showing. We know these all add up to 1, and we really just want, we want at least 1 tail, right? At least 1 tail, that's all of that. But we know that if we add this to this, we have to get 1. So instead of finding all 3 of these, we could just find this 1 and subtract it from 1. Right? So 1 take away this has to be this. So this will, hopefully this didn't make it more confusing. I'm just trying to get you guys ready for chapter 5 when this will come up a lot more. So just the general idea is, if you're ever asked to find at least 1, whenever you see something about what's the probability of at least 1 something, just think in your mind, instead of figuring out at least 1, figure out 1 minus none. It's going to be much easier. This requires 1 calculation. This, if you just do this directly, could require hundreds of calculations. So at least 1, think of 1 minus none. So that should get you, should be good to go for 4.1. So give it a shot, and of course, let me know if you have any questions.